Hey guys, Mr. Z here, Mr. Z on TV, and this time we're going to talk about mixing it up. So, mixing it up refers to mixtures, and mixtures are anytime we take two or more substances and combine them, but they don't chemically combine. In other words, we take hydrogen and oxygen and make water. That's a chemical combination. That's not what we're talking about. We're talking about like if you grabbed a handful of dirt and threw it in some water to make muddy water, that's a mixture. The water didn't change, the mud didn't change, they're just together, okay? So let's get into it. All right, a couple things here. First of all, you can see these dudes here on the left, heterogeneous, homogeneous, the word dissolved, ion, polar, and ionic, and we'll talk about those one at a time. That prefix hetero means different or opposite. So, in other words, a heterogeneous mixture would be like that mud that I described. If you threw the mud in the water and you let it sit there for a minute, you're going to notice that there are particles sitting on the bottom, and they don't look like the ones that are on the top. If I zoom in on this picture right here, it's talking about sodium chloride, which is just straight up table salt, and some water over here. But before we mix it, you can see it sitting at the bottom, and then the water at the top looks different. In other words, this part and this part don't look the same, so we call it a heterogeneous mixture. Where if I look at this little guy over here, which is sugar water, okay, pop that dude up. We could see that over here, once the sugar's dissolved, it makes what we call a homogeneous, or if you've ever read the side of a milk carton, it says homogenized. In other words, it made the milk all the same, top, bottom, the cream doesn't rise to the top anymore. So homogeneous means this. It means that if you look at the top and you look at the bottom, you look at the outside, you look at the inside, you look at right and left and all that stuff, it appears to be the same, appears to be one substance throughout, when in fact is actually two, a solute and a solvent. In other words, particles that are going to dissolve and particles that are going to do the dissolving. So let's take a look at what that means. What does it mean to actually dissolve something? So in this case, we can see most people say the sugar breaks down or disappears into the water. Well, I just sort of alluded to that term, and there's two things you can see, and I'll bring them both of these pictures. Not that one first. Is that the first thing that salt does in this particular case is the salt has to break down. So it goes in these big crystals, and it breaks out into its own molecules. Sodium chloride, okay, you can see Na and Cl, but sodium chloride does something really interesting. It does what we call ionization, and the ions, or particles with a charge, that's what that word means, break into sodium Na plus and Cl minus. And if you notice down here, NaCl does not have an electrical charge on it. That's because the plus up here for sodium and the minus from chlorine cancel each other out, and that's actually the reason why they're together, is because opposites attract. So sodium, chlorine are opposites. When they hit water, they ionize. So we call this compound, sodium chloride, an ionic compound. In other words, it's made from ions. So the first thing is that it must break down, okay? It's breaking down. The next thing that has to happen is when we use that word just a minute ago, homogeneous, that means that it all appears to be one substance. That the part of that is that it spreads evenly. So as we saw, it breaks down over here, and you can see that happening right here with these arrows, breaking down, but it spreads evenly. A lot of people say, well, where does it go? It goes into the spaces between the water molecules, and I'll show you with water. You can see the H2O molecules up here represented with the red and white parts. Oxygen is a negative particle, okay? It's actually -2, which is why it bonds with hydrogen atoms, which are positives. Now, if there's two negatives, there has to be two positives. So hydrogen's only +1, which is why we get two H's, okay? So water is H2O, it's totally neutral, but because it's lopsided, and you can see that here, both hydrogens end up on the same side and the oxygen ends up on the other side, we end up with a positive side of a water molecule, and we end up with a negative side. So if I have my oxygen here, and we said that that is negative, okay, it's actually -2, that's why that looks like an equal sign. And then we have our hydrogens, which are positive, okay, like this. what's going to happen is these positives are going to act positive, and then this side is going to act negative, okay? And I'll show you how that works if you take a look at this image right here. So first thing is we have our sodium. Now this guy right here is a positive ion. So since opposites attract, the oxygen part is attracted to that. Now you can see it up here. Same deal with the chlorine. Chlorines are negative, so they draw the positive side of the water. And this is one of the reasons why they say that like dissolves like. If something is ionic, which means it has positive and negative ions when it hits the water, or if it's polar. Now, polar is another word for how we describe water. Water has a positive end and a negative end, like a battery has a positive and negative, a magnet has north and south, which are opposites. If something is by nature polar, which means it has one end that acts positively and one negative, it'll attract things that are ionic, just like we see here. Positive hydrogen's attracted to the chlorine, and the negative oxygen's attracted to the sodium because they're opposites. Now, if that happened to be another polar molecule, then water would just be attracted, positive to negative and negative to positive. So when something dissolves, it does a couple things. It breaks down and it spreads evenly. It goes into the spaces between the solvent particles. So if it dissolves, ionic things are going to dissolve ionic, same with polar. If something's nonpolar, like oil and water don't mix, people say, what they mean is they don't dissolve, because oil's nonpolar, water's polar. But oil dissolves great in gasoline, because gasoline is nonpolar, and so is oil. Okay, so if we want to really look at what is going on here, it says Tyndall effect. Now, the Tyndall effect uses this. You can see the laser beam there going through two glasses, what look like water. Well, the one on the right is either pure water or some type of solution. In other words, the particles have dissolved and made that solution of homogeneous mixture that we talked about on the last slide. Well, the one on the left is a homogeneous mixture as well. It appears to be the same. I'll grab my own little laser pointer. The top doesn't look any different from the bottom, the right side from the left side, but you can see this laser beam right here. And it shows up, but it doesn't show up here. And so what that tells us is that this one over here on the right has particles in it that are dissolved, because dissolved particles are too small to bounce this light beam around, which is why we don't see it. Kind of like you don't see it in the air either, because the air also is a solution. Particles of nitrogen and oxygen and stuff like that all mixed together, dissolved. Well, these particles are too small to see, which means they won't settle to the bottom. We don't see them collecting at the bottom, but they're actually not broken down. Now, we would still call it a homogeneous mixture because they've spread evenly, just like things that dissolve do, but they never broke down. You and I can't see them with our normal eye until the Tyndall effect reveals them. The light bounces off those particles, and now we can see that they didn't break down. So dissolving means it has to both break down and spread evenly. We call this guy on the left a colloid. And colloids are mixtures. So there's a couple things mixed in here with probably water. But they don't dissolve. Now you also notice that they don't settle. So here's the way to remember a colloid. All right, and a colloid is spelled C-O-L-L-O-I-D. Okay? And check that. All right, so a colloid is something that looks like a solution, usually, not always, but the particles don't dissolve, and we use the Tyndall effect to reveal them. Okay, our last little dealio here is that we have, and this word concentration up here. Concentration is a discussion of the relative amounts of solute, the sugar or whatever, and solvent, in this case maybe water. So if we have sugar dissolved in water, dilute means that I have a lot more solvent than I do solute, not a lot of solute particles. Concentrate means I have a lot of solute particles dissolved in there. So if you've ever heard of, concentrate orange juice, that's made by removing the water. Well, this picture of a sponge, we can see the spaces in the sponge. Now, we said that something like water has molecules, and in the spaces are where our solute goes. Well, there's only so many spaces in the sponge, which means it can only hold so much water. Well, water only has so many molecules, so it only has so many spaces, which means it can only hold, you got it, so much solute. And so what happens is, if we add just a little bit of sugar in water, we would have a dilute solution because most of these spaces over here would remain empty. The more we add, the more concentrate it would become. The more spaces are filled, the closer the particles get to each other. And eventually it can't hold any more. Every one of these spaces you see over here would be filled with solute. And once that's happened, we call that saturated. Okay? So just the same word we use for a sponge. When a sponge is saturated with water, it can't hold any more. And if we add more, that extra water we add falls out. Well, if I had a glass of water and I wanted to put in there the maximum amount of sugar, any that I added above that saturation point, like let's say it'll hold 50 grams, and I add 60 grams, well, if it's saturated, 10 grams is going to sit on the bottom. Then we get to something called solubility. Solubility is exactly what we just were talking about. It's having something saturated, but that saturation point depends on temperature. For example, if you look real carefully here, I'll take this little guy, KCl right here, potassium chloride, and you can follow that graph. Potassium chloride dissolves a different amount, about 27 grams at 0 degrees in water. As it does at 100 degrees, it dissolves about 56 grams of potassium chloride. So it has what we call a positive solubility because it goes up. The slope of the line is positive. Potassium chloride dissolves better under warm water than it does cold. And you can see potassium nitrate, this guy right here, huge change. It goes from 15 off the charts, man. Okay, so that's one of the things we could say. Most of these are positive. But look at this guy, NH3 was ammonia. Ammonia starts off really great, actually, over here at 0. And then as the temperature goes up, it dissolves worse. Now, that's because things that, this happens with gases, okay? Gases don't dissolve as well when you heat the water up because they just have too much energy and gases will evaporate. They won't stay dissolved in the solution. So this is called a solubility table. And these things are properties of their respective compounds. So if you wanted to identify table salt, NaCl, you can see right there, you could say, all right, well, if I have a white powder and I don't know if it's sugar or salt because it wasn't labeled, I could take 100 grams of water, set it at 50 degrees Celsius, and see how much it dissolves. In other words, if I can dissolve more than about 38 grams, you can see right there, then I know it's not salt. So if I took 50 grams, I put it in there, and there's none left on the bottom, it's probably sugar. Because sugar, which isn't on this chart, has a solubility that is way higher than this chart. At 50 degrees, sugar has a solubility over 200 grams. So I can use the solubility of both sugar and salt, because they're properties that don't change unless you change the temperature, to separate them. All right? So I hope that's a good introduction to all the things we've talked about with solutions. And stay tuned for acids and bases. Later.